Today, we're dissecting linear algebra, not the sanitized university version where matrices are clean and datasets fit in memory, but the brutal production reality where your gradients explode, your matrices are singular, and your GPU is melting because someone decided to invert a 50,000 by 50,000 matrix. Three experts who have debugged NumPy losses at 2 a.m., optimized matrix operations for billion-parameter models, and learned why numerical stability isn't just academic theory. I'm Sam, and someone just asked me why their neural network is outputting infinity.
I've spent years optimizing linear algebra operations for deep learning. The gap between theory and practice is massive. Students learn that matrix multiplication is ON3, but in production, you're dealing with sparse matrices, numerical precision issues, and the fact that your simple matrix operation just consumed 40 gigabytes of VRAM. Linear algebra in AI isn't about elegant mathematical proofs. It's about making billions of floating-point operations behave predictably at scale.
My job is making AI models run efficiently in production. Every matrix operation has real costs: memory, compute, energy, and money. When your transformer model has 175 billion parameters, every linear transformation becomes a massive infrastructure challenge. The difference between naive and optimized linear algebra can mean the difference between a model that costs $100 to run versus $10,000.
I've guided teams through countless AI implementations where linear algebra was the bottleneck, not the algorithms. The pattern is clear. Those who understand linear algebra as a systems engineering problem, not just mathematics, build scalable AI. Those who treat it as black box NumPy calls often fail when they hit production constraints. It's about understanding why your matrix operations are slow, unstable, or consuming absurd amounts of memory.
Dr. Martinez guide us through this mathematical hellscape. Maya and Jordan prepare to explain why just use NumPy is the linear algebra equivalent of just use WordPress for enterprise software. No mercy, no hand-waving about eigenvalues.
Let's start with the fundamental misconception. What's the biggest illusion about linear algebra in AI that both engineers and researchers fall for?
And it's just matrix multiplication. People think neural networks are just matrices multiplying inputs, but the reality is vastly more complex. You have numerical stability issues, conditioning problems, sparse versus dense operations, memory layout optimizations, and the fact that floating-point arithmetic isn't associative. Every operation compounds errors. What looks mathematically equivalent can behave completely differently in practice.
The abstraction trap. Engineers think frameworks like PyTorch or TensorFlow handle all the complexity, so they don't need to understand what's happening underneath. Then their model trains slowly, consumes ridiculous memory, or produces NaN losses, and they have no idea why. Understanding tensor shapes, memory layouts, and operation fusion isn't optional for production AI.
Why is linear algebra so central to modern AI, and how has this relationship evolved?
Everything in AI reduces to linear algebra. Neural networks are compositions of linear transformations and nonlinearities. Backpropagation is computing gradients through matrix operations. Even attention mechanisms are just fancy matrix multiplications. The evolution has been toward larger and larger matrix operations, transformers with massive attention matrices, billion-parameter models where individual layers have gigabyte-sized weight matrices.
In hardware acceleration, GPUs are essentially massively parallel linear algebra machines. The entire modern AI stack, from CUDA kernels to tensor cores to specialized AI chips, is optimized for matrix operations. Understanding linear algebra isn't just about algorithms. It's about understanding how your code maps to silicon and why some operations are 1000x faster than others.
Give me a concrete example of a linear algebra pitfall that destroyed a production system.
Gradient explosion during training. A team was training a deep network and gradients kept exploding to infinity. The culprit, they were using matrix inversions in their custom layer, and the matrices were becoming singular due to poor initialization. Matrix inversion is numerically unstable. Tiny perturbations in input can cause massive changes in output. We replaced inversions with pseudo-inverses and added gradient clipping. Numerical stability isn't just academic theory.
How do these numerical stability issues manifest in practice?
Vanishing and exploding gradients, NaN losses, models that train perfectly on small datasets but fail at scale. The classic example is matrix multiplication order. A times B times C versus a times B times C are mathematically equivalent but can have drastically different numerical properties. Condition numbers matter. Badly conditioned matrices amplify numerical errors exponentially through your computation graph.
And it impacts inference speed. Poor numerical choices during training create models that are slow or unstable during deployment. I've seen models that work perfectly in FP32 but completely break in FP16 because nobody considered numerical precision during development. That's the difference between deploying on expensive V100s versus efficient edge devices.
What are the most critical linear algebra concepts that AI engineers consistently misunderstand?
Matrix rank and conditioning. Engineers use matrices without understanding their fundamental properties. Low-rank matrices have special structure you can exploit for compression. Ill-conditioned matrices amplify errors. Also, eigenvalue decomposition. It's not just academic theory. Principal component analysis, spectral normalization, understanding optimization landscapes, they all require eigenvalue intuition.
Memory layout and cache efficiency. Row major versus column major storage affects performance by orders of magnitude. Matrix multiplication algorithms like GEMM aren't just about computational complexity, they're about how data flows through memory hierarchies. Understanding tensor strides, broadcasting, and memory coalescing is crucial for GPU optimization.
Let's talk about dimensionality. How do high-dimensional spaces break intuition?
The curse of dimensionality is real and brutal. In high dimensions, almost all points are approximately equidistant from each other. Nearest neighbor search becomes meaningless. Random vectors are nearly orthogonal. Your intuitions from 2D and 3D completely break down. This directly impacts embedding spaces, distance metrics, and why naive similarity search fails in high-dimensional vector databases.
How does this affect practical AI systems like recommendation engines or search?
Embedding vectors in production are typically 512, 1024, or even 4096 dimensions. Cosine similarity becomes less discriminative. You need dimensionality reduction techniques, approximate nearest neighbor search, or hierarchical clustering. The naive approach of computing all pairwise distances scales quadratically and becomes computationally intractable. Understanding high-dimensional geometry is essential for building scalable similarity search.
What about optimization? How does linear algebra connect to training neural networks?
Optimization is linear algebra. Gradients are vectors in parameter space. The Hessian is a matrix of second derivatives. Gradient descent is vector arithmetic, but the devil is in the details: preconditioning, second-order methods, natural gradients. Understanding the geometry of lost landscapes requires linear algebra intuition. Why does Atom work better than SGD? It's about adaptive scaling of the parameter space.
How do you handle the massive scale of modern AI models?
Model parallelism and distributed linear algebra. When your model has 175 billion parameters, it doesn't fit on a single GPU. You need to partition matrices across devices, synchronize gradients, and handle communication overhead. Understanding how matrix operations decompose across distributed systems becomes critical. Techniques like gradient accumulation, mixed precision, and activation checkpointing are all linear algebra optimizations.
How is the field evolving to handle these scale challenges?
Sparse matrices and structured sparsity. Not all matrix operations need to be dense. Pruning techniques create sparse weight matrices. Attention mechanisms can use sparse patterns. Block sparse matrices, low-rank approximations, and factorized operations reduce computational complexity. We're moving toward more intelligent matrix representations that exploit structure.
Hardware co-design. Modern AI chips like TPUs and specialized matrix multiplication units are designed around specific linear algebra patterns. Understanding how your mathematical operations map to hardware capabilities determines whether your model runs efficiently or burns through compute budgets. The future is about matching algorithmic patterns to silicon capabilities.
What about automatic differentiation? How does backpropagation actually work?
Automatic differentiation is computational graph traversal with linear algebra. Every operation in your network has a Jacobian, a matrix of partial derivatives. Backpropagation applies the chain rule by multiplying these Jacobians in reverse order. Understanding this isn't just academic, it's why certain network architectures are efficient, why gradient flows behave differently, and why some operations are expensive to differentiate.
How do you debug linear algebra issues in production?
Monitor condition numbers, track gradient norms, check for non-propagation, and understand your matrix properties. Use tools like matrix profilers to understand computational bottlenecks. Visualize weight distributions and activation ranges. Most linear algebra bugs manifest as performance issues or numerical instabilities that are invisible until they cause catastrophic failures.
Profile memory usage and computational patterns. Understanding whether operations are memory-bound or compute-bound requires linear algebra analysis. Tools like NVIDIA Nsight and profilers that show tensor operations help identify bottlenecks. The goal is mapping mathematical operations to hardware utilization and finding optimization opportunities.
How do you ensure reproducibility with floating-point operations?
Floating-point arithmetic isn't deterministic across different hardware or operation orders. Parallel reductions can produce different results. We use deterministic algorithms, fix random seeds, and understand that mathematical equivalence doesn't guarantee numerical equivalence. Reproducible research requires controlling the entire computational pipeline, not just algorithm parameters.
What about adversarial robustness? How does linear algebra connect to security?
Adversarial examples exploit the high-dimensional geometry of neural networks. Small perturbations in input space can cause large changes in output space because of how linear transformations amplify directions. Understanding eigenvalue properties, Lipschitz constants, and the geometry of decision boundaries is crucial for building robust AI systems that resist adversarial attacks.
How do quantum computing and linear algebra intersect with AI's future?
Quantum computing is fundamentally linear algebra in complex vector spaces. Quantum algorithms for linear systems, matrix inversion, and eigenvalue problems could revolutionize certain AI computations. But current quantum computers are noisy and limited. The intersection is promising for specific optimization problems, but we're still years away from practical quantum advantages for general AI workloads.
Holy shit, so linear algebra isn't just math class torture. It's the foundation of every AI system, the source of every performance bottleneck, and the key to understanding why models work or fail catastrophically. This is computational physics, not just matrix multiplication.
Welcome to production AI. Anyone can call a PyTorch function. But understanding why your matrices are ill-conditioned, your gradients are exploding, and your GPU utilization is terrible. That requires deep linear algebra intuition combined with systems engineering expertise.
This episode was brought to you by Engineer Panic, where we expose the mathematical reality behind AI hype. Because understanding why your neural network produces none losses is probably more important than debating which transformer architecture is trendy. We're back, let's talk about the practical nightmare of mastering linear algebra for AI. Maya, what's the most counterintuitive advice for engineers?
Stop avoiding the mathematics. I see engineers who can implement complex neural architectures but panic when they see an eigenvalue. Linear algebra isn't optional background knowledge, it's the language of AI. Spend time understanding matrix properties, not just matrix operations. Learn to think geometrically about high-dimensional spaces.
Profile everything. Don't guess why your model is slow, measure it. Understanding whether operations are memory-bound or compute-bound requires looking at actual hardware utilization. Every matrix operation has costs in time, memory, and energy. Optimization without measurement is just wishful thinking.
Build intuition through implementation. Code matrix operations from scratch, understand why certain algorithms exist, and learn to recognize numerical stability issues. Reading about condition numbers is different from debugging a model that produces none losses because of poor matrix conditioning.
What are the biggest red flags in how teams approach linear algebra?
Treating frameworks as black boxes, using operations without understanding their computational complexity, numerical properties, or memory requirements. Also, ignoring precision, assuming FP32 and FP16 behave identically, or not understanding how quantization affects matrix operations. These abstraction leaks cause production failures.
Premature optimization versus premature abstraction. Teams either micro-optimize irrelevant operations or use inefficient high-level abstractions everywhere. Understanding when to optimize and what to optimize requires deep knowledge of how mathematical operations map to hardware. There's no substitute for understanding the full stack.
Ignoring the fundamentals. Eigenvalues, singular values, matrix norms, these aren't just theoretical concepts. They directly impact model behavior, training stability, and computational efficiency. A solid foundation in numerical linear algebra prevents countless production issues.
How do you stay current with advances in numerical computing for AI?
Follow hardware development's new GPU architectures, tensor processing units, sparse matrix accelerators. Read numerical analysis papers, not just ML papers. Understand how algorithmic advances in linear algebra translate to AI performance improvements. The field moves fast, and mathematical innovations directly impact practical performance.
What keeps you up at night about linear algebra education in AI?
The growing gap between AI popularity and mathematical understanding. Students learn to call PyTorch functions, but can't debug when those functions behave unexpectedly. We're creating a generation of AI practitioners who can't reason about the mathematical foundations of their systems. That's dangerous for building reliable, scalable AI.
The assumption that frameworks solve everything. High-level abstractions are powerful, but they hide complexity that eventually surfaces in production. Understanding linear algebra isn't academic luxury, it's operational necessity for building AI systems that work reliably at scale.
That we're optimizing for demo performance instead of production robustness. Models that work on clean datasets with perfect numerical properties often fail catastrophically in real-world scenarios with noisy data, hardware constraints, and adversarial inputs. Robust AI requires robust linear algebra.
How do you test linear algebra components without waiting for full model training?
Unit tests for matrix properties condition numbers, rank, eigenvalue distributions. Synthetic data that stress tests edge cases, ill-conditioned matrices, near-singular systems, extreme scaling. Profile individual operations in isolation. Build intuition for how mathematical properties translate to computational behavior.
Final advice for engineers who want to master linear algebra for AI.
Start with fundamentals, but immediately connect them to practical problems. Implement basic algorithms from scratch: matrix multiplication, eigenvalue decomposition, SVD, then profile and optimize them. Understanding why certain algorithms exist and how they behave numerically builds the intuition you need for production AI systems.
Think about hardware and systems, not just mathematics. Every matrix operation runs on silicon with specific characteristics. Understanding memory hierarchies, parallel processing, and numerical precision isn't optional for production AI. The best AI engineers are part mathematician, part systems engineer.
Debug real failures in production systems. Nothing teaches linear algebra like tracking down why your model produces none losses or why your optimization diverges. The constraints and challenges become visceral when you're responsible for fixing them at 3 a.m. Build systems, measure everything, and never stop learning the mathematics.
This has been Engineer Panic. We've learned that linear algebra is the invisible foundation of AI, that numerical stability isn't academic theory, and that understanding matrices deeply is the difference between AI that works and AI that fails catastrophically. Sweet dreams, and may your eigenvalues always be well conditioned.
Thanks for the mathematical reality check. Now, if you'll excuse me, I need to figure out why our transformer model is somehow computing negative attention weights, which should be mathematically impossible.
And I need to explain to my team why our simple matrix multiplication is using 90% of our GPU memory, and why switching from FP32 to FP16 made our model completely insane. Also, why our optimization just diverged to infinity.
Keep building, keep measuring, and keep connecting mathematical theory to practical systems. The future belongs to engineers who understand that AI is applied linear algebra at massive scale, not magic.
This has been Engineer Panic, where linear algebra meets production reality. Until next time, remember, your AI model isn't broken. Your matrix operations probably are, and the solution requires more than just switching to a different optimizer.